Hi all, welcome to this channel. We have a Discord if you would like to join us. There's also a website built using Obsidian Publish that will have all the scripts, including the rough drafts. Notes made during the week will also be put online on this website. You can also vote for new projects when we are finished going through the book. In the meantime, there will be weekly YouTube videos, so you're more than welcome to stick around here for a while. Let's examine a new data type called const. It is an immutable data type that has certain restrictions. We declare it using uppercase letters. We can still have underscores between words. We cannot use data that is built during the runtime of our program to create them. The data must be constant data. We can still use expressions on the constant data to create these variables. The list of constraints are listed in Chapter 17 of the Rust documentation. Const is used for global variables we can access in any scope. It is recommended to store your global variables in one place by the Rust book. I remember hearing issues about Toyota's cars having too many global variables. They had over 10,000 global variables stored in the software and people couldn't figure out what was causing issues. I read a couple of places on the internet and the recommended maximum number of global variables was 10. We will now talk about different methods variables can appear from instead of being created. Rust has a technique called shadowing. It allows you to reuse a variable name inside a scope without reassigning the variable name outside of that scope. This feels like a method to avoid issues with having too many names for different versions of the same data with modifications applied to it. I also wonder, does this prevent some kind of computing problems where people tend to mutate data in multiple different scenarios? If people are altering data with multiple functions, keeping track of the form of data you have could be an issue. It is better to assume that the data is always of one particular form perhaps. To use shadowing, we say let variable name equals some expression in a scope. Then we can use that name in an alternative context. My first time seeing this felt odd to me. Why is this useful? To build intuition and understanding about this, I decided to Google how people use this technique in practice. I found out that people use shadowing when dealing with sanitized data they receive from the internet. They still wish to retain the old data, but using it could be dangerous. Rather than coming up with new names, they just shadow the old data with the sanitized new data. This prevents multiple names for the same data. A downside could be that we have not distinguished what stage of processing the data is at from the name. Something I found interesting is that there is no restriction on data type when using shadowing. If my original data type is an integer, I could shadow it with a boolean without issue. I thought there may be some restriction, but it seems not. This may change later. In summary, I believe the purpose of shadowing is to allow for scope-related actions where we want to keep the original data. Programming can be used to build systems to respond automatically to situations. However, different scenarios require different responses. Control flow is how we match the response to this scenario. We have different methods of control flow depending on the structure of the event. The methods of control flow we will be exploring are if, else if, loops, while, and for loops. I found it surprising that Rust has ways of returning values from control flow methods, such as loop. I have not seen that in other languages. We will begin with if statements. These are used when we wish to apply an operation if a condition is satisfied. Let's take a string. We take alternative actions for different types of words. For instance, if our string here is a name, we capitalize the initial letter of names. So if string is a name, string equals capitalize initial string. Other situations also have capitalization. For instance, if we have a capital city, rather than repeating if statements, we can use an else if statement. This way, anytime the situation is satisfied, we stop after taking that action. If statement can also be used to assign values to variables. It has the following syntax: let variable equal condition, else. It is restricted by the fact that outputs in each case need to be of the same type. I've seen this in a video on building a website with Rust. We may be in a situation where we have an unknown amount of times we have to perform an operation. It could be even indefinite. We could have a program that keeps responding to the input from a user. An example is how people use ChatGPT. Loops are a method of control flow designed for this. We've seen this in a guessing game. There are a couple of features of loops I find interesting. We can return values from loops. I am unsure of the current use for this. Next, we can name loops. Then, when we are breaking from loops, we can decide which loop we wish to exit from. The while loop is also used for indefinite processes. There are certain features that are different between them. Loops will always run once, whereas while loops may not run. While loops cannot be used to return values like loops can. Lastly, we cannot name our while loops. Loops seem to be an efficient way to write while true. Apparently, there are times where you wish to do this, and compilers have made efficient code based off of this. The last method of control flow that we'll be talking about is for loops. These occur when we are taking a repeated action for a known amount of iterations. An example is capitalizing every letter in a string. The number of times we capitalize a letter is the number of letters in the string. This will have a fixed length and we can repeat the same function on each letter as we progress. An important part of programming is how we store data. The method of storing data is known as memory allocation. There are two kinds, heap and stack. It seems that languages tend to use both. The book mentions that stack is faster. Let's talk about the structure of each and to see why. For stack collection, data is stored in order, one after the other. To access the data, we proceed backwards through the data. For heap, we figure out a place to store the data and then allocate our data there. Let's compare these with the analogy of storing books. Stack collection could be viewed as storing books one on top of the other, like a stack. In a system, you can add a book to the top layer or remove a book from the top layer. Note that there is a limit to how far you can stack the books before toppling over. This seems to correspond to the concept of stack overflow error. We cannot indefinitely add to the stack. In heap collection, if we're storing your book in a library, you need to find space for it with some ordering system. To access it, you need a reference to find it. To access multiple books, the closer they are, the faster you can find them. Stack allows for faster retrieval, but heap allows for more complex organization. Rust has a new method of memory allocation to prevent issues that commonly occur from arising. The concept is called ownership rules. The rules are, each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. This is going to have a significant impact on how we conduct our memory management, especially with functions. We'll start with copying data. There are two ways of copying data in Rust, shallow versus deep copies. A shallow copy is where we create a second reference to the same piece of data. A deep copy is where you make an exact copy of that data. Let's talk about this with a homework example. Suppose we have two people, Aoife and Tadhg, where Aoife has done the homework. We say that Tadhg has a shallow copy of the homework if he just borrows it whenever he needs it. They pass it back and forth as required. We say that he's made a deep copy if he transcribes it. This highlights some issues with shallow copies. Suppose Tadhg borrows the homework and then writes on it. If Aoife tries to use it, she'll find her notes change in potentially unexpected ways. How Rust deals with this issue is that if you relabel the data, it moves its ownership over. In this case, if Aoife passed the homework to Tadhg, Tadhg is now the owner of it. Rust by default tends to shallow copies for performance. Rewriting the homework is far more time-consuming than simply passing it over. One exception to this is integers. Integers are deep copied. Then how does this interact with the rules of ownership in Rust? For example, in the homework, if Aoife passes the homework to Tadhg, the homework is now Tadhg's. Whenever ownership could be shared, the last variable to own it is the permanent owner. Whenever we want to create deep copies of data such as strings, we can use clone to do so. Let's look at functions. When passing our data as it is into a function, we can be transferring ownership. Let's look at an example here. Let's use examples to show some ownership rules. We will enclose the owner of a variable in a yellow box to highlight where the ownership is. To start, we will have a function that takes a number and then prints it out. We will name that function drop variable. For now, we're going to assign a variable a name. We assign 5 to x, so the ownership of this 5 is x. Then we fill our variable into our function. Note that the ownership of 5 now goes into the function. This prevents there being two owners of a variable. Now we apply the process of drop variable. At the end of the function, the ownership goes out of scope. Now we cannot access it even inside the main function. Let's now see how to transfer ownership of a variable with functions. The function we will use is called lose and take. We will use it to show how to transfer ownership. To start off, we will assign 5 to x again. We will use it to show how to transfer ownership. Let's see how to transfer ownership of a variable with functions. The function we will use is called lose and take. We will use it to show how to transfer ownership. To start off, we will be assigning 5 to x again. Here x is the owner of the variable. Then we pass it into our function so it travels within the function scope. When it passes to return x, we are transferring the value back out of the scope. This means our 5 from the start is now assigned to s instead of x at the end of the function. We want to use our variables without changing them, so we'll need a process to use our variables in our function without losing ownership. Borrowing is a technique to solve this. This refers to passing the reference of a variable into the function. I will use yellow boxes to show ownership and blue boxes for references. Let's show this through an example. Our example will be to take a number and print it out. We will call our function printNum. So we have a function followed by printNum. Then we add our parentheses. Then we add our variable into the function without ownership. So we add an ampersand before the variable. Then we use the function as we would like within the function. This leaves the ownership outside of where the function is. Let's examine functions where the variable can change. So we wish for a variable to be mutable. We put mute before our variable and the ampersand before the mute keyword. This makes our data mutable. Note that this does not become an output for a function. Let's test this idea out. We will make a function that increases the value of an integer by 1. We will call it add1. We have fn followed by add1. Next, within the parentheses, we have ampersand mute followed by the variable. As we have no output, our function notation is complete. Then we take our variable and add 1 to it. The ampersand means that the only reference that enters this function and not the ownership. We need to make sure that we put a semicolon at the end to ensure our output is a unit. Rust has rules on references to prevent errors. We will focus on how Rust prevents the data race error. This error occurs when we are trying to write on one piece of data from more than one place. This leads to bugs when both are trying to alter the data simultaneously. To prevent this, Rust makes restrictions on variables where we can mutate the data. Therefore, mutatable data has restrictions on them. Immutable variables don't. The restriction on mutable variables is designed to prevent two or more variables accessing the same mutable data. Rust prevents this by having mutable data having only one owner. For immutable variables, data racing cannot occur. There is no benefit to placing restriction on the number of variables that have access to the data. So we don't. Here is a summary table of how Rust prevents data racing. Thank you for watching. There's a Discord link below as well as a Twitter. If you wish to examine either notes or scripts, the Obsidian Publish is attached to. You can see scripts and plans for the next videos there. My GitHub is linked below too. Looking forward to seeing you next week.